and then also testing and evaluating our models, which is obviously a big part of machine learning, right? You want to know how your model is doing after training, and you want to know what you can do to improve it, right? They're two really big, important components. So essentially, what we're going to be looking at today is first we're going to be talking about cross-validation, what it is, why it exists, and what its purpose is. And then we're going to be talking about we're going to be looking at an example of cross-validation in a data set of like test scores. And we're going to be using a simple linear regression on that data set after performing some cross-validation on it. So essentially, the fancy definition of cross-validation is any sort of validation technique that is used to estimate how a statistical test will perform on an independent sample. So that might be a bunch of words, big words, right? But essentially what that means is we're just going to be looking at sampling a part of the training data set and using that as sort of a pseudo-independent testing data set. If that makes sense. So let's think of it like this. Sam, you're recording, by the way, right? Okay. So let's think of it like this, right? So we have this training data set. Let's say we're working on something related to patient data, right? So we're working with a bunch of patients who maybe have some sort of disease, and we're trying to figure out if we can, our deep learning can, our machine learning can classify or diagnose this patient automatically without having a doctor come in based on a bunch of input features. So if we have the data set, and say we have 1,000 patients in that training data set, and we have maybe 200 in the testing data set, right? So out of that 1,000, if we were performing a cross-validation procedure, what we'd essentially say is, if we're using a specific type of cross-validation called k-fold cross-validation, which is the main thing you need to know, which is the main cross-validation procedure you need to know. It basically says this: when we ask to split that training data set into portions, we're going to split that training data set into portions, and then from each of those portions, all the portions step one as a training data set, and that last piece will be the testing or the validation data set in our training data. So say we have 1,000 patients in our training data, and say we want to perform 10-fold cross-validation. So what that means is we're going to take out 1,000 patients, divide that by 10, so it's going to be 100 patients in each fold. So what we're going to say is one of those folds is going to be the validation set, and the other 9 are going to be used for training. And essentially, we can randomize which 10th is selected. So it's basically, as long as your training data isn't biased, you're basically randomly sampling from the population, right? Because if your sample of training, if your training data, that sample is unbiased and representative of the population that your machine learning model is going to represent, and randomly sampling from that will still provide you with the sort of this smaller patient group that is still representative of the larger population. So the validation set is still going to be unbiased. So yeah, that's kind of the big picture, or the big sort of idea behind validation. So like I mentioned, there are two main types, or two main functions that you'll be using. So the first is the k-fold cross-validation. The other is the stratified k-fold cross-validation. So k-fold cross-validation is basically just what I described. You start with a training data set. You basically divide it into k subsections. So whatever you specify k as, could be 5, could be 6, could be 10, whatever. So you divide your data set into those different pieces, and you essentially will make all of them. You randomly select one of those pieces and make that the validation set, and then everything else will still be the training data set. So yeah, and so that's the simple k-fold cross-validation. So now let me quickly explain what stratified k-fold cross-validation is. So say that you have a data set, right, and you have a bunch of features, but you have some sort of relationship between some features that you want to maintain in between your training and testing I'm sorry, into your training and validation set. So essentially, let's think of it like this. So we have some I don't know variable that we want to maintain the split between in that variable. So I'm trying to think of a good example here. So let's say we have I don't know. Oh, I have a good one. Say we have a training data set that is slightly biased in terms of how many. It's not biased, but the labels or the class labels are unbalanced, which means that say you have binary classification, right? You're trying to classify whether someone has a disease or not. In your training data set, say 70% of people have the disease and 30% do not. Obviously, that's unbalanced and likely unrepresentative of the entire population. So when you train your model on that training data set, you want your validation set to kind of maintain that 70-30 ratio, right? Because that's you're gonna see in the rest of the training data set. So in order to like make sure that happens, and you aren't, because with regular k-fold cross validation, you're randomly selecting different patients for that same example, right? We're just randomly selecting different patients and using those in our validation set. But here, with stratified k-fold cross validation, we can basically say we want to group these patients by this variable or this feature. In our case, it's actually going to be the class label, which is essentially what if it's binary classification, whether they have the disease or not. If it's multi-class classification, then it's one of the different categories. So that's a really good example of how when you want to maintain the proportions of class variables between the validation set and the training set. That's a great example of when you would use stratified k-fold cross validation. So now that I've talked a lot and I probably talked a bit fast, does anyone have any questions about just what I just said?
Nope.
Nope. Okay, so it makes sense. That's good. All right, so now we're going to take a quick look at a Google Colab to do this. Okay, so I have to pull this up. So give me 1 second. Where's this notebook? Okay, here it is. Okay. All right, so here's a great example from, I think I took this from Code Basics, which is a really good website. Why can I not share my screen? Let's try this. Can you guys see my screen?
Yep.
Do you guys see the GitHub, or what do you see? Do you see my desktop or the GitHub?
The GitHub.
Cool. Yeah, so this is from Code Basics, which is, again, like I said, a really cool website. So they have a cool Python tutorial where they go through using cross validation with a bunch of different machine learning classifiers. So essentially, the first thing they do is they use this really handy function, which we've seen a lot, which is this train test split, which essentially allows us to split our initial data into a training set and a testing set. And you might notice that, if you guys remember way back when we started talking about Python syntax, this really cool property of Python where you can sort of pass the different variables that you want assigned to. So the train test split outputs, this function outputs for basically lists or arrays based on the dimensions of our data. So essentially, it's technically arrays slash matrices, I guess. So yeah, it would output, the first one would be the basically all the input features for the training data set. And then would be testing. I'm sorry. Next thing would be all the input features for the testing data set. And then ytrain would be a vector of one column that would just have the different class labels for the training data set. And then ytest would be the class labels for the testing data set. And in here we specify, right, this data set called digits, which I'm assuming is going to be some sort of number recognition data set. So you sort of look at the different digits and figure out what number they represent. I think that's what it is. The data set is. Yeah, I think it is. That's what I'm guessing it is. All right. Anyway, so they specify the test size is 0.3, which means 30% of the initial data will go into the testing data set. So now, right here, we have our training data set and testing data set already separated. But so we still have to separate the training data set into the validation set and the actual training set. That makes sense. So there are a bunch of different machine learning algorithms that we can perform. The first is not machine learning. It's just a simple regression. So we're going to use logistic regression first. And generally, something I actually wanted to talk about, which I actually haven't gotten the chance to talk to you guys about. Whoops. Okay, you can still see my screen, right? Okay. One thing I want to talk to you guys about that I haven't actually talked a lot about is that sometimes machine learning is not the answer to the problem you're working on, right? Maybe you're working on something that can be solved better mathematically with an algorithm. Sometimes, like I said, machine learning just isn't the best solution. You may not have the training data. You may not have the problem you're looking at may be too complex for machine learning because with the amount of data you have, it may be inefficient. There are a multitude of reasons why machine learning may not always be the right answer to the question you're working for. So sometimes logistic regression is sometimes better. So here we create a simple logistic regression model and we score it and we get a pretty nice score, 0.91. And here we use an SVM, which we talked about already. And we do the same thing. We fit the training data set and then we score the testing data set, and we get a little bit of a worse score. With random forest, we get a score that's quite equal to the logistic regression. So we're satisfied with using the random forest algorithm, right? Because it performs a little bit better than logistic regression. So we'll use that. So now let's get into how we use cross-validation. So first of all, you import kfold or stratified kfold from sklearn.model _ selection. So this is sort of the library where you import kfold from. And then you specify that k. So k is going to be denoted by this variable n splits. So you specify n splits equal 3, 5, whatever. And you can also specify random state, which is essentially a parameter which you can use to make sure that the cuts or subsections that you take are repeatable. So say you specify random state equals 100. If you say you run this kfold splitter on the same data set on a different computer, but with the same random state number, it's going to produce the same splits. So random state just ensures repeatability. And lastly, you can shuffle the data before you do it. So you can specify shuffle equals true. But we don't specify these last two parameters, so it's going to split it just based off the number of splits we gave it. So now, since we asked for 3 splits, we're essentially going to be going through all the splits in the first dimension, so the first 9 of them, and we're going to be printing the training index and the test index for all of them. And now we're going to be basically rerunning the same 3 algorithms or three algorithms: logistic regression, SVM, and random forest, but with cross-validation. So as you can imagine, right, if you have, you might be wondering why we need to run this. So this part is pretty straightforward, right? They're just doing the same thing they did up here. You might be wondering why when you run this do we end up with 3 scores, right? So the reason why this happens is if you think of it, right, when you split that data set into 3 parts, with cross-validation, we're essentially running the algorithm 3 times, right? Because we're specifying this fold is going to split by. So we're running the algorithm 3 times, and in each time, we're denoting a different subsection or different split as the validation set, right? So we basically have 3 different validation sets, and therefore 3 different training sets essentially. And when we run those, we get 3 different scores. And generally, when you use cross-validation, you usually get an average score or a weighted average score using these subscores. And that's what you report on a research paper or whatever kind of project you're doing for your results. Yeah. So here we manually implemented cross-validation, but of course, scikit-learn is always very handy, and they already have a cross-validation scorer for us. So again, we can do it in one line and get the exact same results. So yeah, that's basically it. And here we tune it a little bit by using the cross-validation score to see how well the algorithm does, because we specify different numbers of estimators, right? And we see that the increased number of estimators, we're getting slightly better, but then as soon as we go from 20 to 40, from 30 to 40, we see that it kind of decreases a little bit. So we're probably going to stop at 40 and not go to 50 for the number of estimators. And yeah, that's a quick basic example of how cross-validation works. So any questions?
So you said cross-validation gives you a score of how well it does. At what point did you use this score to improve the model?
Yeah, so that's a really great question. So you might be saying at the beginning I talked about the reason why we do cross-validation is because it allows us to improve our algorithm, right? But you might be wondering what exactly can we garner from that score to figure out what we need to do to improve. So essentially, when you're setting up any sort of machine learning or deep learning algorithm, as we'll talk about, you specify a bunch of what are so-called hyperparameters, which are essentially just variables that you pass. For example, for the random forest classifier, right? The hyperparameter for that is the number of estimators, which is essentially the number of trees you want in your forest, decision trees, right? And so that number you actually can't you might have an intuition on what's overkill or what's not, but the only way to figure out what number of estimators works well is to actually just test it. So the cross-validation score will give us a good estimate of how the model is performing with different numbers of estimators or with different number of hyperparameters, and without having to go through and look at the independent testing set. If that makes sense.
Okay, cool.
Okay, Anika, Victor, any questions?
Can cross-validation be used to correct biased data, or is it just fitting whatever's in your training set?
Yeah, like I said, validation is just the goal of validation is just to randomly sample from our training data set, from that training split that we made, right?
Okay.
So if that training split we made is biased, then our validation set will likely be biased, because essentially we're just randomly sampling from that.
Okay, got it. Thanks.
That's why actually a large part of machine learning is just getting data that works well and understanding how to create a pipeline that is negates or mitigates a lot of the bias and impurities that might end up in your algorithm.
Mm-hmm. Okay.
All right. Anyone have any other questions?